Okay. All right, so so today I'm going to talk more about TDA and machine learning and sort of give an overview, and then I'm going to kind of go back to discuss some of the foundations of topological data analysis, things like what's the detail in computing persistent homology and so on and so forth. But this is my second lecture for the week where I want to give a flavor of machine learning in combination with TDA with the hope that this will help students formulating maybe final project in that direction. But before I do that, I want to address one of the question 2 lectures ago. I ran out of time last lecture, but I want to actually address this. There is a more detailed question over what is the relation between those homology of sort of check complexes versus RIPS complexes when I'm actually doing inference of the coverage. And then this is really the nice paper that you should read about. It's fairly easy to read. It's really just called homological sensor networks. I'm just going to zoom in and so on and so forth. And it's done by 2 of the researcher that really, one of those folks that really pioneered this area of using sort of homological notions to study sensor network coverage. Okay, so but the specific in this paper, the specific serum that is most important to the result I discussed earlier is what's called Serum 5. Okay, so this Serum 5 is really what I said is that if I am computing RIPS complex, why is it approximating the behavior of check complex? Okay, this is called believe it or not, this is called the squeezing theorem. Okay, so is the squeezing theorem is basically because of what we showed earlier in the lecture, is that remember at a certain parameters that in the range of parameter, the check complex, which is the middle part, the C, the check complex, is sort of nested between a pair of RIPS complex with a particular radius. Okay, and what's happening in this case is that there is sort of a ratio between the radius that is sort of sandwiching the check complex. Okay, so when you because of this sort of nesting behavior or sort of squeezing behavior, you can actually look at Serum 5. A Serum 5, of course, there's a few notation I need to explain. X is sort of the nodes, which is the sensors, and it's in a domain. And remember this theorem, the beauty of it, it's talking about sensors in any dimensions. It's not just 2-dimensional sensor, it's actually d-dimensional sensor. And then there's a bunch of properties that talk about those sensors, which is earlier in the paper. And I'm not going to go to detail. If you're interested, you want to look into it. And then he says the sensor cover, the domain, contains the restricted domain, D minus C, if the induced homeomorphism, I'm not going to describe homeomorphism in this class, but we'll go back in the future classes. It's just a nice mapping between homological classes is non-zero. Okay. So essentially, what does this map do? It's looking at, if you look at this, it's looking at a form of RIPS complex. The F part is the boundary, what they call fence sensor, the fence of the coverage area. So for the time being, imagine it as sort of the boundary of the covered region. Okay, so this is sort of this is really a relative homology, but also again, I don't want to explain what a relative homology is, but really think about each of those terms as the homology of a region and ignoring anything outside the boundary, right? So that's what this homology means. And it says, if the maps between the homology of the RIPS complex is sort of have a nice mapping across 2 different sort of radius, then there is a nice statement I can make about coverage. Okay, so what does this mean? Why do we want this? Is that this is actually a perfect paragraph right here that describes the motivation why we want to use RIPS in place of check in actual computation, right? So this is ideal. This nesting is ideal for engineering applications. The RIPS complex is computable because remember, you only need pairwise intersections or pairwise distances, but it does not give an accurate representation of the topology of the cover, okay? The check complex gives the exact homotopy type of the cover, well, / homology, but it's not computable with the coarse information available from the network, okay? So then it move on to say this sort of nesting behavior at different scale is really as a result of persistent homology, okay? And it concerns homological properties of nested families of topological space, okay? So essentially what we are going to come back to this kind of mapping between homological groups in later part when we go into the theoretical foundation of persistent homology, right? So again, on the high level, based on the theorem on this page, all it's saying that is instead of trying to compute the homology of the check complex at a fixed radius, I'm going to compute the evolution of homology of RIPS complex between two separate radius. And that's what this theorem means. Okay, so I want to give you this, and I love this quote to end this discussion. It says, topology, the stratosphere of human thought. In the 24th century, it might possibly be of use to someone. The later part was kind of depressing, but the first part was actually really important. But the good news is that we did not have to wait until the 24th century to do topological data analysis. Okay, all right. Now, any questions so far? Okay, all right. So, oh yeah, let me conclude this part. Is that when we look at evolution of homology, this is also the key part of bringing theory to practice, because really the key notion of persistent homology is that when I look at data, there may not be an exact resolution that I can infer the structure of the data. Instead, there may be a range of resolution I want to infer the data, such that when I'm studying the evolution of the structure under the range of the parameter, I will learn more about the data than if I were going to pick a fixed parameter, like a fixed scale. Okay, so it's a very important philosophy that is very applicable for especially when your data is a point cloud sample of the underlying space. So if you're not careful, if you just want to choose one parameter to infer it, that parameter may not be good enough because of sampling density and because of noise and so on and so forth. But instead you say, okay, instead of fixing one single parameter, I'm going to look at the range of parameter and look at sort of persistence behavior of the structure over the range of parameter. That will be really nice for me to recover what is really underneath the process that generate the data. So we're going to see more examples as we go along, but that is a very important philosophy. And sensor network coverage is sort of have a flavor of that. All right. So, okay. So today let's go back to TDA and machine learning. And my point for today's lecture is that deep learning is not only seen in machine learning. Machine learning is such a big field that I want to give a quick sort of high level view of what machine learning is, if you have not taken a machine learning course, but also kind of start having people think about what topology can help in various machine learning models. All right. Okay, so this is going to be my very, very course level review of sort of the general field of machine learning. It's not going to be comprehensive at all, but if you actually go online right now, there's a lot of courses online that is targeted towards people want to learn machine learning. So this is really just like a machine learning in a nutshell. So roughly speaking, when you look at machine learning algorithms, that you can think about there's really roughly 3 types, okay? The first type is supervised learning. So supervised learning is that you have essentially data with labels, and you train your model with those labels. For example, if I have sort of a bunch of image data, for example, from cancer images, right? Like, you know, kind of image data where you say, okay, all these images corresponding to brain tumor, and all those images corresponding to people without brain tumor. So I have sort of a classification problem that I train my classifier over those label data. And now I have a new image, and I want to say, okay, given this new image, can you predict whether this is someone with tumor or without tumor? Okay. So, a classic in supervised learning, there's 2 types. One is classification and one is regression. Now there's a second type where my data don't really have labels on them, right? So the type of question I'm going to look at is, well, can I do some sort of clustering, right? If I have a bunch of sort of say genetic profiles of a particular sort of I don't know, primates or something, and then you want to say cluster them based on those genetic profiles, maybe to study phylogenetic trees and so on and so forth. So another aspect of unsupervised learning is that you have, for example, high dimensional data set, like, you know, maybe very high dimensional, but the idea is maybe I want to be able to reduce the dimensionality while still preserve some structures. And when I reduce dimensionality, it's easier for me to kind of, again, understand maybe what's the underneath structure in there. And then the last one is sort of semi-supervised learning, which is basically that, you know, maybe I have a partial label data, what I'm going to do with that, right? So it's not complete label data, but partially ordered, but I can still do things like classification and regression, okay? So I would say that in all those 3 aspects, you know, potentially that you can have a very topological perspective to it, because really, as I mentioned in the first lecture, that a lot of machine learning model ultimately is trying to learn some sort of shape that best fit the data. And when you talk about the shape of the data, there's 2 things coming to mind. What is useful to describe shape? One is geometry and one is topology. And geometry describes things like curvature, and topology describes things like connectivity. Okay. Now, well, let's look at sort of a different kind of way to categorize existing machine learning models, right? I mean, the link I provided here provide a lot more detail, but this is really a very high level picture of roughly what things are. But I really like those pictures. I didn't generate them. But it's a very good sort of mental picture to have when you think about those machine learning models and algorithms, because those pictures are very, I would say, geometric and topological. They all have shapes in there, okay? So the first aspect, remember, is regression analysis. And, you know, remember we talk about this particular mental picture when you have a bunch of points, and then your linear regression is try to find the best fitting line or best fitting hyperplane, right? And then the idea is, you know, in some sense, you want to reduce the distance to this boundary, okay? So where does topology play? Topology really can help me decide what this boundary is. What is it? So this is, think about this as things like decision boundary in a certain way, or, you know, sort of separating plane. And in fact, we do have examples how very recently topology has been used to help improve those decision boundaries or sort of regression study. There is examples of sort of instance based algorithm, and let me go to this link here, and it will give you a more detailed. Okay. What's going on? Oh, man, one of those. Sorry, just bear with me. This is a problem with my, okay, hold on 1 second. Let me do something different. Okay, I'm going to share a different screen. Okay, so in here, there is, this rough clustering, rough classification, and then there's instance ones. And then we're going to talk about some of, maybe we have time to talk about a few of them, but things like K-nearest labor, self-organizing map, support vector machine can all be considered as instance-based algorithms, okay? And then there are really sort of a decision problem with instances or examples of training data. The next one is regularization algorithms, which is things like ridge regression and lasso. If you use that before, it's least absolute shrinkage and selection operation, and so on. And it's basically used to try to, it's part of, like this large class of regularization algorithms. And then the one that I put here is sort of that is most sort of popular. And then there's this decision tree problems where you actually, this picture is really nice to have a sort of, you start by training your model. For example, the classic example is if you have data coming from diabetic patients, and then they have sort of different measurements like weight and height, diet, sort of other sort of medical record, and you say, okay, is this person, which age is this person, younger than 65, above 65, you go to each part of the decision tree. And then that's how you also train the decision tree to try to adjust the weights of each branches. And then once you have it trained, if you have a new patient coming in, you can just follow the path from the root to a leaf to kind of predict, for example, its risk, and so on. So decision tree also is really interesting because it's one of those type of models that is interpretable, meaning that once you have trained a decision tree, you can, and when you fit it with testing data, you can actually, once you have a prediction on this new data point, you can actually explain to people to say that, why did I make this prediction? It's because, okay, this person is above age 65 and is about more than 200 pounds, and so on and so forth. So as you follow the decision tree, you can actually explain a rule that is used to explain your prediction. So there is really some sort of idea is that if you can use those kind of, in another way, a decision tree is a type of interpretable model in a sense that you can actually interpret its prediction. So there is a certain branch of research is trying to use interpretable machine learning model to approximate sort of things like deep learning models in a way that you can use interpretable models as a surrogate for hard to interpret models or black box models, so that they have exactly same type of prediction, but you can interpret the prediction using the interpretable model. Okay. There's also the class of the Bayesian algorithms and things like naive Bayes and so on. And then in there, you basically, the important part is to do to provide sort of a prior estimation of the distribution of the data, and using that to infer the posterior distribution. There's a really large class of clustering algorithms of, again, things like K-means, K-mediums, and hierarchical clusterings. In fact, today we're going to spend a little bit of time talking about a few of those clustering algorithms. And to be fair, right, this is going to be, I have to warn you, this is going to be a very biased statement, that clustering is essentially a type of topological question. right? As I mentioned before, clustering is really find sort of connected components in the data. And that is inherently a topological thing. So I actually still hope that there's a lot more newly development of using topological notions to develop new clustering algorithms. Okay. And then of course there's a association rule, learning algorithm. Those are not too popular, but it's there. It's looking at sort of relationships between variables in the data. And then there's also this large class that has been expanded upon, things like perceptron and neural networks, and it's a large class of machine learning algorithms. Last lecture, we gave example of how you use topology to kind of probe a deep learning model. Okay. Oh, sorry. In here, this classification, they separate those two classes because they specific say, okay, there is artificial neural network. A really representative is a perceptron. But then the deep learning part, where you are talking about very deep neural networks, and he kind of separated into a more separate class. And then, of course, you have seen convolutional neural network, which is what we see in Inception V1, contain many CNN layers. There is recurrent neural networks and so on and so forth. I mean, the class of neural network is really expensive right now. And then they are used in sort of image, text, audio, video classification tasks and regression tasks. All right, so, and also, like I said, I think this area, if you can bring in topological and geometric notion, it's actually a really actively research area. Okay, the next one, dimensionality reduction. You might already, how many of you have used PCA before? Right? Yeah, so I mean, PCA is one of those examples of dimensionality reduction, right? It's kind of reducing high dimensional point to low dimensional projection, where preserving the first few dominant directions, right? But there's also the other class of, there's a boom of dimensionality reduction techniques in the sort of early 2000s, where there is a large collection of dimensionality reduction techniques out there. This list is not that complete. I would say there's a few very widely used ones. One is TSNE, TSNE. And one is, well, the most recent one is called UMAP. But the interesting thing is that both type of algorithm works pretty well in practice, but there's actually still not sufficient understanding of its theoretical properties. Okay, but people love to use them because they do show pretty reasonable results in practice. All right, so that's dimensionality reduction. And then there's also ensemble algorithm, which is interesting, which is essentially you can have a machine learning model that is composed of multiple weaker models. And essentially your final prediction is sort of combine the prediction of all the weak models together to get your final prediction. Random forest is part of this type of model. And of course, there's other machine learning models that is out there, but this is a good sort of initial classification of the machine learning model you will see in the literature. All right. Okay, so like I said, there is a few interesting questions. For example, in here, I said there's a few things that's not on the list is TSNE and things like UMAP. And there is a really interesting conversation between pure mathematicians and practitioners recently about UMAP, because UMAP is in the paper says that it's inspired by a branch of mathematics called category theory, and people who are pure mathematicians got super excited and is trying to understand the precise connection between category theory and UMAP, and then it's still an ongoing debate. How much can we claim UMAP to be a success story of category theory? All right, so those are just quick comments over how, if you go to scikit-learn, a lot of those algorithms, I think with exception of like, I think perceptron is actually in scikit-learn, but if you're doing deep learning, there's other packages like PyTorch and so on and so forth that is, not really at the core of a scikit-learn, but the interesting part about scikit-learn, if you go to the following link, it gives you kind of a cheat sheet for how you apply machine learning models. And I'm sure this is a little bit out of date a sort of cheat sheet. But the idea is you have the starting point, right? And then you kind of move along. Do I have enough data? No, then go back to get more data. If I do have data, then if I have label data, if you have less than 100K, then I'm going to do certain type of classification on the left corner. And if I have, if I have category data, what I'm going to do, things like spectral clustering and so on and so forth. If I care about the quantity and it's more of a regression issue, I go to sort of the type of area to do regression tasks. And then if I am going to really get a quick overview of my data to see how they're distributed, I can maybe apply dimensionality reduction. Okay, so it's sort of like a guidance when you have data. How do you follow this kind of? I mean, of course, this flow chart isn't necessarily the perfect thing because there's always exceptions, but at least it gives you a rough idea of how you can actually apply machine learning algorithms to your data set, depending on the type of data you have. Right? But the whole goal of me giving this high-level picture of machine learning algorithms is the fact that I would like to think about how is topological information can be utilized in a machine learning model. There's roughly between 2 and 3 type of categories, depends on where does topology sits with respect to the machine learning model, either exterior or interior or something in between, right? So the first type, which is used a lot in sort of regression and classification tasks, is you compute topological features and you use them as input to a machine learning model. The classic example in here is to say, let's say I want to classify a bunch of materials, okay? And let's say I'm focused on some sort of high throughput nanomaterial. What I'm going to do, or nanomaterial or sort of small molecules, what I do is for each of those molecules, I'm going to derive, say, compute its persistent homology. And it's going to give me some sort of vector. And there's various ways to vectorize sort of a persistent diagram. Let's say I turn it into a vector. So that became my topological feature vector. Then I can fit it to a classifier to use that topological feature to help me with my classification tasks. You can do it just using topological feature vectors, or you can combine topological feature vectors with some other classic feature vectors. For example, in material science, you can combine it with other type of geometric measurement of the material and so on. And you can do that for sort of classification, okay? So this is roughly classified as using topological features as input to a machine learning model. So you are kind of, topology sits in the exterior of that model, okay? So that's the first type. The second type is using topology as internal knob in a machine learning model. So for example, if I'm using example as a regression as an example, in classic regression, you always have some sort of, let's say Y is, let me just, for the time being, and, right, like something like this, so somehow this is sort of, a sort of model for the data. Let's say this is a linear model, but here this is sort of, or maybe like a penalty term, okay? So that penalty term in most recent work in the past 3 or 4 years, if I want to bring, say, topology into the model itself, I can actually use this as a penalty, like some sort of topological penalty. So what is a precise example for that? And we'll come back to this later, but I want to give you a quick example. So in image sort of segmentation, if I have sort of a picture of cell like this, then my goal for image classification is to say I want to segment different pieces as different cell boundaries. So this is one cell, This is another cell. And let's say this is a third cell. Okay. So I want to be able to kind of take the image of the cell image and to be able to segment the cells out. But if I'm focusing on the cell boundaries, sometimes when I extract it, I might get something like this. Okay. So because of the image quality and everything, so ideally, for example, in this simple example, I should really segment it like this, where the left-hand side is one cell and the right-hand side is another cell. Okay. But when I say a topological penalty is that even if my cell boundaries is not really dividing those two cells, I can put a topological penalty term to say that I'm going to enforcing the segmentation to enforce there are two cells, okay? But how do I enforce that? One way is to say I'm going to enforce the dimension 1 homology, because if I just care about the boundary, I'm going to enforce the segmentation result such that the dimension 1 homology, which is beta 1, is equal to 2, where 2 is some preset number. Okay, so this is one very simple way to enforce topological information in my model, where I'm going to put a penalty term that if my final segmentation in this very simple case does not give me two loops with respect to the cell boundary, then I'm going to have a penalty, right? So, and so on. So basically you want to enforce certain agreement with my prior knowledge of the homology of the image. And then you are going to give a penalty if that does not align well with your homological understanding of the data. That's just really a high level example of what is the internal knob in a machine learning model using topology. But of course, if you're thinking about, you know, if your model contains sort of stochastic gradient descent, then there's potential ways to also bring topology to describe the behavior of the gradient. Okay, so that's going to a much complicated model. The last one is I'm going to use topology to probe the output of a machine learning model, or maybe intermediate output of the machine learning model. Then the example is exactly like Topo Act, which we talked about from last semester, last lecture, where basically I'm probing the intermediate behavior of the model by collecting the activation vectors, right? So I would say this is some sort of interfacing topology with the machine learning model. It's not completely exterior, it's not completely interior. So I kind of put it in the third category. Okay, so when you think about this, then the major question you want to ask yourself, right, if you are thinking about sort of final project, is to say, okay, if I want to kind of combine topology with some sort of machine learning model, is how do you want to interface the topology with it? Okay, so those are really different ways this can happen. And then later in the semester, we're going to see more and more examples that spans all three categories. Okay, so I'm going to come back to clustering, because clustering is sort of one of those really classic area. It's also a very messy area, meaning that there's a lot of folks from very different disciplines that care about clustering and are deriving new algorithms from clustering. One example is people who are in social science. There's a lot of clustering techniques that coming from social science, because you want to study sort of a grouping of entities in the society. Things like similar things with sort of the area of people studying network science or social networks. But anyway, let's go back to the core of that. And again, in here, I need to kind of click on, I'm going to use my screen again, because I should have done just a second. I would like to share my other screen. Okay, so I'm just going to share the screen here. Can people see the page visualizing K-means clustering? All right. So K-means clustering has this interesting thing is that what is the idea of K-means clustering, right? And this is a nice visualization of it. So basically what you have is you say, I have a bunch of points. And of course, in this case, is that I'm going to have, let's say I'm going to have the smiley face as my data point, okay? And what you do is, let's say I have, let's say my K is, I don't know, 3 roughly. And then what you do is you first choose some random center, and you're going to assign points to its nearest random center. Okay, so this is what you have. So now K is equal to 3. So all the points that is close to my initial choice of red point is red. Green points close to the green point is green, close to the blue point is blue. And then I'm going to update my centroid according to those 3 classes. So I'm going to recompute the centroid of the colored points. So now you have recomputed. And now you're going to reassign points based on its association with its nearest centroid. So now the label of the points has to be updated. So you reassign the points. And then again, you do this iteratively. Okay. And reassign, recompute, reassign, recompute, reassign. And you do this until it converge, right? So of course, because of one of the drawback of K-means is what is K. So obviously, when I choose this particular algorithm here, because it's a smiley face, so there is the eyeball, the mouth, the face, right? So in a way that 3 is definitely not enough. So basically, ideally, if I say I want to, I don't know, add more centroid and so on, and I'm going to restart. Oh, sorry, I should have done. Let me do it again. Let's say I'm going to add, let's say I will add 5, okay? And as I go through, right, the initial thing, you can see that depends on how my initial assignment is, it also affects my final results, okay? So K-means is one of those very widely used clustering algorithm, but depends on your randomization, how your initial choice of the points are in your centroid, it's going to affect your final results. Also depends on what is the K is, it's going to influence your final results, okay? But nevertheless, there's a really interesting property of this algorithm is that it's really saying that I am starting with some initial guess of a cluster centers. And I'm going to iteratively update the cluster center until convergence. And that is the cluster we have, okay? And of course, even in this case, when I choose 5 initial clusters, because my initial choice is not choosing around where my mouse or eyeballs are, you are actually still getting a very, not very ideal segmentation of the data, okay? So, but that's one of the classic algorithms that people have. Okay, so the next one is that, okay, so basically, well, I'll go back to my slides afterwards. Let me go to restart. I want to, so here, if I do, I will choose pinkly smile, then I can do my initial choice, right? This is assuming I have some maybe prior knowledge of my data. Let's do this. Okay, if the user is choosing it, well, it's still not good enough, I must say. But at least in one of those green eyeballs, I was able to kind of concentrate and focus. And then there's also what's called random chosen one, which is the one we just did, right? This is, when I just do random choice points. But then there's also the farthest point, which is basically the idea. Let me just use a different cluster. If you choose one point, and the next point you choose as initial centroid has to be one that is furthest away from the current one. So you find another one that's furthest away, and then you find the third one that is furthest away from both. Okay, and then in this case, of course, this data is pretty nice, so kind of converge very quickly. Okay, so essentially, what are the sort of the parameters that's influencing? There's k, number of centroid you choose, and then the location of the initial thing, and you can choose randomly, or you can choose with some prior knowledge, or you can choose with furthest points. So you can play with the with animation to get a sense of how K-means clustering works. So let me get back to my slides. Okay, so as I mentioned before, depends on how you choose. You are going to have different initial choosing centroid, and it will converge differently. And then the second thing is result of it is very much depends on your initialization steps, right? So where is your initial seeds are is going to influence your final results. So basically, if you want to have a good understanding of your data, maybe you want to do a bunch of random initializations and looking at a collection of the results. But the whole reason that you can talk about K-means clustering, this is sort of the algorithm steps. If you have, Faye, can you mute? I think I'm hearing a bunch of keyboard typing here. Okay, so if I have a high dimensional points, the idea is to partition it into k number of clusters, where k is typically much smaller than the number of points. And then it's basically a minimization of intra-cluster variance. Okay, so what is this thing do? Is to say that, let's say I have, say, 3 cluster things, and you have, let's say, data points like this. Let's say this is my point X, right? And then there is a nearest assignment of cluster center. Let's say this is mu of 1. You want to sort of minimize the sum of distances for all points with respect to their nearest centroid, okay? So you want to really minimize the sum of square distances. And this thing here is also, this is really, this potentially term is a sum of square distance to the centroid that is assigned to, can also be written as the size of that particular cluster times the variance of the cluster, where this is the mean of the point in that cluster. Okay, so in a way that K-means clustering is also reframed as minimizing intra-cluster variance. Okay, so there is essentially, as the animation is showing, there is a few steps. The first step is initializing the centroid, which is really computing the mean. You can choose it by a user, you can choose randomly, or you can choose based on farthest point. And then you can do the assignment where for every single point in the point cloud, you want to assign it to the nearest centroid. Okay, that is a mathematical notation, but just to say assign to the nearest centroid. And then recompute the centroid, that is step 2, which is update step. You just compute essentially the average points, okay? And then you repeat until convergence, where you can no longer, your assignment is no longer updated. However, as you see in the example, it does not guarantee convergence to the global optimal, okay? So that is the K-means. There is a variation of K-means. It's called K-means plus plus, and it differs from K-mean by the initial step. The high-level idea is we would like to spread out the initial K cluster centroid as much as possible. The first step is you choose a point, a centroid, uniform at random from the point cloud. And then for every single point in the remaining of the point cloud, you compute the distance to this nearest centroid at this that's already chosen. And then your third step is you choose one new centroid from the point cloud at random as a new centroid using a weighted probability distribution where the point is chosen with probability proportional to this distance. Okay, so what does this mean? That means every single point can be potentially chosen as a new centroid, except that the point who is furthest away from existing centroid is the one who is going to be chosen with higher probability. Okay, so there K-means plus plus basically have this sort of stochastic process inside where we say that, you know, really all points can be potentially chosen with as centroid, but I'm going to give high probability to the points that is furthest away from all the other centroid. Okay, and then again, you repeat steps until all the initial K centroid has been chosen, and you apply the standard K-means clustering. Okay, and K-means plus plus has shown to perform pretty well. Again, this is a really bad link, but you can find it on Wikipedia to describe all the details, but it's really at the core of it is initialization. Okay, so before I go on, here is a quick idea. I haven't realized it, but here's a quick idea of how to connect K-mean and K-means plus plus with homological idea. Okay, before I say what I think might be an interesting thing to think about, do people have an idea how, if I have an algorithm, right, like a clustering algorithm like K-means plus plus, what is a potential initialization I can do to help me figure out what is K, and also to help me figure out what is initial seeds or the centroids? Any ideas?
Maybe we can compute the persistent homology, right?
Yes.
Like varying the radius and find the 0th Betti number.
Yep.
And use it as the number K.
Yep.
And we can put centroids to each component of the data set.
Yeah. Yeah, so that's true. However, you can also argue this might be a chicken and egg problem, right? If I can already compute sort of the homology where how many clusters do I have, maybe I don't even need to do, maybe I don't even need to do clustering any longer, right? But this is a good mental exercise, right? So you can compute either persistent homology, or you can estimate, right? So maybe, right, for computational efficiency, I might not want to compute the homology of the entire point cloud. Maybe I can just estimate it. So what I can do, I can subsample the bunch of points, right? You know, let's say I'm going back to my smiley face. I have points like here, points like here. Let's say, I mean, for some simplicity, I just have those three things, right? If I want to recover maybe the homology, maybe I only need to choose like a reasonable sample of it. Like even in this case, I just choose a sample of like, say 9 points. But hopefully I'm, you know, like my sample is based on some density estimation, whatever. I can sample my point cloud and kind of estimate what is my basically Betti zero, right? What is number of components I have? And that will help me to pick K, okay? So that's one way where potentially topology is going to give you some information. The second thing, if you look at K-means plus plus, what does K-means plus plus do? It's trying to spread the initial centroid to be far away from each other, okay? But then there's an obvious homological question. If I know there is a few components based on my estimation, maybe I can choose my initial centroids based on the connected components of my data, okay? Of course, again, this is a chicken egg problem. If I already know there's 3 components, why do I even need to do clustering? I already have that, right? So in other ways that to some degree, when you compute persistent homology, you're already doing some sort of proximity-based clustering, okay? So this is something you really have to keep in mind. Ultimately, persistent homology, even though it's keeping track of the homological changes over time, inherently, it's the clustering algorithm, right? That's why I want to describe clustering algorithm first to get a sense of the connection. So in some sense, persistent homology as an algorithm is already computing clustering, okay? But it's a sort of a slightly different notion of proximity because it's actually more closely related to hierarchical clustering or single linkage hierarchical clustering, which it will show up later when we talk about persistent homology. But if I just want to think about, kind of have a quick exercise of how to inject topological idea in this very classic clustering algorithm, is if I can kind of get a good initial sample of the data, I can use that to estimate what K is based on homological information. How many clusters do I have, right? The second thing is I can also choose my initial cluster centroid based on those connected components, right? So basically I choose one point and I said, well, my next point has to be in a different connected components. And my third point has to be the third connected components and so on and so forth. So that's a good thing to think about when you think about injecting topology into an existing model. Now, the second model I'm going to describe is called dbscan. You have seen dbscan before from lecture on Tuesday. It's a density-based clustering of points, and it's actually won the Test of Time award in KDD 2014 is because it's so simple, but it's also very effective. High-level idea is that you group together points that are closely packed together, right? So when points have many nearby neighbors, you're going to group them together. And then you mark points as outliers that lie alone in a low density region. So basically what are those outliers is those points whose neighbor or nearest neighbor are too far away. Those are outliers. And again, in the high level, you still need to spread out the initial K cluster centroid to run dbscan. But K is not, it's something that will change over time based on the density. So the algorithm itself, you don't really ask for specification of what K is. So the initial thing is I have points X, and I have a parameter epsilon, which describes the radius of a neighborhood. So if I have points like this, and if my epsilon is this parameter, then the points A and B is a neighbor of C. So you basically think about draw a ball of radius epsilon in surrounding point. And the minimum point is a threshold, and think about this as a threshold of sort of a density threshold, okay? So your starting point is you have a few definitions, what's called a core point and what's called density reachable points and outliers, okay? A point is a core point if at least minimum points, number of points is within distance epsilon from it. So let's say, for the time being, let's say my minimum point is 5. Then a point, let's say this point X is core point if you have at least 5 points. I actually drew 6 points. If you have at least 5 points in a neighborhood of radius epsilon, okay? And reachable is a reachable point if it's within epsilon point from a core point. So all the point in this disk is density, is sort of density reachable, right? Because it's close to a dense, it's in a dense region, okay? And the last one, and then the third different sort of notion is a path. A point P is reachable, a point Q is reachable from a point P if there is a sequence of points so that they are all within some sort of epsilon balls between them. So basically what this means there is sort of a continuation of pretty dense regions going from one point to another. So those are reachable. And then of course, when points are not reachable for any points are called outliers. So for example, this point is going to be an outlier because in this epsilon neighborhood, there's no other reachable core points. So those are outliers. Okay, so this is a high-level picture of dbscan. And what dbscan does is it just union those regions that is high density, and that's it. Okay, so this is high-level algorithm. If a point is a core point, then it forms a cluster together with all its points that is reachable from it. And each cluster contains at least one core point. And non-core point can be part of a cluster, but it's kind of the edge, right? They are the edge point because they cannot be used to reach other points. So if you look at dbscan, it actually has quite a bit of a flavor of a covering, okay? So what do I mean by that? Let's say this is, actually you can see it later on in a animation. Remember I have this point cloud of somebody's face, right? In K-means clustering, this is bad because no matter how you do K-means clustering, if, even if you just choose say 5 centroid, K-means clustering is going to give you 5 cluster because it's going to enforce the partition of this point cloud into 5 different clusters based on the algorithm itself. But for dbscan, what it does is it's actually, assuming, let's say my minimum points, let's say my mean point parameter is like 3 or whatever, or maybe 5, then you are basically covering it with neighborhoods where each of those neighborhoods contains 3, let's say 3, the way I drew is actually 3, contain at least like 3 points or something to that effect. So each of those thing here has a core point, okay? So because of the way this is designed, all those neighborhood of the core point, they are all reachable from each other. So they are going to be merged into one cluster. So if I run dbscan over this point cloud, it's going to return one single cluster because it's merging multiple cover element that is considered to be very dense. And when I say cover element, I mean those epsilon neighborhood surrounding points that is dense. Okay, so it has a very interesting flavor of a cover. And this cover showed up in the mapper algorithm we described in lecture 2, in lecture 5, okay? And then the second thing that is really interesting is this is really a density based algorithm, but it actually has this sort of growing philosophy to it because you just say, I start with some core point and I'm going to grow my neighborhood to go to all the other reachable core point. So it also has this kind of evolutionary, it's an evolution of underlying merging of essentially merging of those cover element, okay? So you can see that this is inherently topological too, but also dbscan is used in mapper as a subroutine to do clustering to find connected components in or cluster of my points. The reason why we use dbscan is I do not have to specify initially how many cluster I want, which is important in the mapper framework. Okay, so this is the pseudocode of dbscan, right? You have the parameter epsilon, you have the minimum number of points. For every single point that is unvisited, we're going to mark it, visited. If it's within certain sphere, if the certain neighborhood is smaller than the minimum number of points, I'm going to ignore this point. So this point is in not so dense region. Otherwise, I'm going to expand the current cluster, right? So this pseudocode is basically saying that is my point an outlier? If it's not, if it's an outlier, I'm going to ignore it. If it's not an outlier, I'm going to start expanding the cluster based on the current dense region, okay? So I'm not going to go into detail, but this is really, it's important to go over this to really understand what dbscan does, but it's as described on the high level. So now I would like to go back to, of course I can't click. going to go to just a second. It just requires a little bit typing. We saw the visualization of dbscan. Let's look at the visualization. Oh, sorry, Kmeans. Let's do the visualization of dbscan. Okay. So you share. Okay. So here is a dbscan. Let's again do a simple smiley. And go to restart. Oh, wait, I want to, let me do smiley face. Epsilon, let's say my epsilon neighborhood is, I don't know, this is adjusting neighborhood size. Let's say this and go, okay? So as you see, this is starting from some initial seed point, and I'm going to expand based on reachable core points, and you just keep growing, okay? And then most likely this is going to keep going until all the high density core point neighborhood are all merged together, right? And then that is going to return the outline of the face as a single cluster. And when that is done, it's going to check, are there remaining points in my data set that has not been assigned a cluster, and go start from there. So now it starts from the mouse cluster, and it's going to grow in sort of regions. Yeah. And then, the eyeball, and then the left eyeball. Okay. So the idea is quite simple. All that is saying is that I'm pretty much on the high level, consider my point cloud to be covered by really dense region. And when all those dense regions are nearby, meaning that they're reachable from each other, I'm going to merge them. Okay, so that is a rough idea. And I can go back to say density bar, right? For example, in here, what happened here is that my underlying density underlying cluster has very different density thing, and then you kind of grow, and then you see most likely it depends on the density thing. You see how this cluster stop growing is because I choose a very small radius, and I also choose a very high density threshold, meaning that if it doesn't reach that density threshold, it's going to stop. Stop the current growth. Okay. So again, why do I want to show dbscan? Well, dbscan is used, so now it's actually trying to detect a bunch of outliers, right? All this point is considered outlier, and it's just keep detecting, okay, is this point dense enough? No, 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 no. And you just keep doing that until, it reached some relatively dense region. For example, those dense regions were returned because, you had at least 4 points. And then, all those points that is not in a cluster is considered outlier. And then it's the dbscan just ignore them, okay? So the reason I want to describe dbscan is because, again, you see homology in this picture. Right? So it's actually kind of a random initialization. It's kind of say, I start with a dense region and I'm going to grow the dense region. So now the question is, how do you bring specifically, let's say, persistent homology into this picture? I mean, this is brainstorming, right? Like, where does homology come in? So one idea, sorry, go ahead.
Oh, no, I was just going to say
yeah.
that you're growing your connected components similarly to homology, and seeing, if it actually can merge with some other connected component, then it, eliminates it and creates a single piece.
Yeah, that's exactly right. So essentially, it's remember in persistent homology, we are sort of growing union of balls, right? We're kind of looking at intersection between balls, and that's really inherent to dbscan too. It's really saying that, well, of course, dbscan has remember the difference of dbscan. dbscan has a fixed radius. Okay, dbscan is fixed epsilon, and persistent homology increases epsilon over time, right? So in a sense that dbscan is always capturing the homology of the underlying space at a fixed radius. This is what you see on the left. At a fixed radius in the current thing, it's going to return me 4 clusters, okay? But because of the nature of this data, at this radius, this data also has a loop, right? Which is a phase, okay? dbscan is not aware of that, but it's a consequence of taking the union of points at this particular radius of choice. Okay, so in a sense, again, now you see dbscan, it also has a bit of a flavor of homology and persistent homology. Okay, so again, what I can do, remember the animation I was showing, dbscan always start with one initial point, but you don't have to. You can start with some initial point, and you can again choose initial point based on your initial estimation of the homology. Maybe your initial estimation isn't perfect, but remember dbscan will merge clusters when they actually are dense enough and close to each other, right? So one potential way to try to bring homology into this picture is to say, let me sample some initial points and estimate how many clusters are there. And in fact, I'm going to sort of use those initial sample points that belongs to different kinetic component to be as initial seeds. Okay, so that's where topology can go in. I mean, of course, I don't think people has written paper in this direction because, like I said, there's again a chicken egg problem. But it's interesting to think about a topological notion when you look at those classic algorithms. All right. Yeah, go ahead.
In the dbscan demo you were just showing us, I saw like 2 seemingly disconnected points that are assigned the same cluster. Why does that happen?
Yeah, that's because, let me go back. Let me just share that screen back. Here, right? So
yeah,
this
like that green bit over there.
What's that?
Like the green part on the right side, it's assigned to the same.
So I think most likely there's multiple points here. There's at least 4 points, but you don't see all of them. Even though it looks like there's only 3, I think because remember I said my minimum cluster have to have at least 4 points. So most likely there's at least 4 points in here, or actually 5 because it's 4 nearest neighbor, right? So it's happened. Yeah, go ahead.
My question is, why is it the same cluster as the bunch of green points in the middle?
Oh, no. This is actually 2 different clusters. It's just the visualization happened to choose the same color, but they actually are separate clusters.
Oh, okay.
Yeah, that's just an illusion because the visualization has a fixed number of color that it's drawing from. So for example, this red cluster and this red cluster is actually 2 separate clusters. They just color them the same.
Okay.
Yeah. So yeah. Ultimately, you are faced with some sort of full coloring, like map coloring problem, right? You want to choose color and you want them to not be the same color. But yeah, this is just an artifact of the visualization.
Okay.
All right. So I want to get back to, now you have seen 2 of the algorithms. Oh, wait, it's going to take a while. Okay. So you've seen Kmeans, you see dbscan. Both algorithm has a flavor of persistent homology and homology, right? So which actually makes you wonder, can I use, I mean, not necessarily those 2, right? There's a very large collection of algorithms in clustering. Can I use my knowledge or my estimation of the underlying topology of my initial data set to help initialize the algorithm or to help improve the algorithm, right? So those are some interesting thoughts to have. And then let me get back to Mapper. Of course, I would not be able to go through my 50% of other slides that I was planning to do, but we'll cover that next class. Is that where does Mapper algorithm, right? This Mapper algorithm we kind of had a flavor of in Tuesday's lecture. Where does it fit in the machine learning landscape? Well, number 1, it's unsupervised, okay? Number 2 is actually a clustering algorithm. Okay, so in a sense that, you know, this popular tool is actually by itself, you know, kind of unsupervised. It's actually unsupervised learning algorithm, and in fact, it's a clustering algorithm. In fact, specifically, it's a function-induced clustering algorithm. Okay, so I want to give a comprehensive review, and then those are the two papers that I'm relying on. And I'm just going to, maybe with remaining time, I can only talk about the history of this. You know, the paper came out in 2007, so more than, you know, roughly 13 years ago. It's actually at the core of many data analysis startups. But I was checking recently, some of those companies has been kind of bought by other companies, right? But Yasti, I think, is still alive and well. So essentially, the Yasti is funded by two of the authors of the original Mapper paper. And it's at the core of the company's sort of algorithm itself, and is combined with sort of machine learning and visualization. And then there's also Apine data, which is, you know, they a few years ago, they had a talk about try to do topological data analysis at scale. There's also another company, which now I think I'm not sure what's the fate of it. But the idea of it is that there's enough interest from the industry to looking at this, because partially it's appeared to be very useful in practice to look at data of complex nature. I wouldn't have time to play those videos. I would encourage you to watch them. They're basically sort of Yasti's sort of PR-facing way of describing the Mapper algorithm, okay? But it's kind of cool because, you know, I think it's a very exciting for people who work on computational topology and topology data analysis to see how something came out of this field, became something that is actively used in the industry, and you know, why, you know, in some sense topology matters, right? I mean, this is sort of the ultimate success story of a tool that is developed in theory and moved to practice. So it's very exciting. The video, you know, the Gunner's video initially talk about why topology is interesting, and then move on to describing the Mapper, and then right-hand side is talking about like risk prediction in finance. And specifically, this is a video I would encourage you to watch. It's talking about, you see this picture, looks familiar. This is a Mapper graph, and it's used to kind of looking at patient stratification in medical data set, okay? And then, of course, there is another talk by Apine Data that also, if you see the picture on their talk, this is, of course, 4 years old, but it's again talking about the Mapper construction. But then here they are looking at how to do scalable analysis using those topological tools. And specifically, they are trying to use Spark, which is sort of a database system, right? To how to combine this with database system to achieve scalability. And then, of course, you know, there is really nice property associated with Mapper algorithm that we're going to go into detail next lecture. What I'm going to do is I'm going to describe, you know, what is a mathematical foundation to the Mapper algorithm, and what are some remaining open questions to understand the Mapper construction. Okay, but that would be a good point to stop. And I'm going to